I hope you're not one of those people that just memorize definitions without knowing exactly what they mean. So here in question 4, the only question I would understand if you got it wrong is 4.5. That is the only question that I think was a bit difficult. Everything else is just basic stuff. So let's go ahead and look at 4.1. We're supposed to define the term impulse. Let me show you something. We know fully well that F net is equals to the change in momentum divided by the change in time. If we cross multiply, the change in momentum or the impulse is equals to F net multiplied by delta t. So what is the definition of impulse? If you look at this formula, the impulse should be the product of the net force and the time it acts on the object from the formula. That's the connection you need to make between definitions and formulas. That is 4.1. Let's go ahead and take a look at 4.2. Use the information on the graph to determine the magnitude of the impulse as the ball hits and bounces off the force sensor. Right, let's go through our question statement and see what is going on. When a ball hits and bounces off a surface, it exerts a force on that surface. Grade 12 learners investigated how this force varies over time as the ball hits a force sensor and bounces off. A 50-gram softball was dropped from a height of 1.5 meters vertically above a force sensor connected to a laptop as shown on the diagram. And the graph we're given the force versus the time. The force is in Newton and the time it is in milliseconds. So as soon as you don't realize that the time is in milliseconds, you're probably going to get the question wrong. Let's use the information in the graph to determine the magnitude of the impulse. So the impulse is the force multiplied by the time. We have a shape, we have a triangle. So in order to find the impulse, we need to find the area of this triangle. How can you find the area of a triangle? That is half base multiplied by height. So this will be equals to a half base. Our base is the time in milliseconds. We go from 0 to 15 milliseconds. So we're going to have 15 divided by 1000. Multiplying by 10 to the minus 3 is the same as dividing by 1000. Now we have converted our time from milliseconds to seconds. Multiply by our height. Our height is right here. We are given the value as 64.13. So we have 64.13. That is the impulse, half base times height. If you put that in your calculator, you'll get 0.481 newtons multiplied by seconds. That is 4.2, calculating the impulse. 4.3, state the magnitude and the direction of the change in the momentum of the ball. The impulse is equal to the change in the momentum of the ball. So we already have our answer. We just need to quote it. Right, we need to state the magnitude and the direction. So the magnitude is 0.481 kg meters per second. Why am I using kg meters per second? Because when you are calculating the change in momentum, you use the mass and the velocity. So that's why I have kg meters per second. But when you calculate in impulse, you have newtons multiplied by second. That is the only difference. Right. So we have 0.481 as the magnitude. What about the direction? The ball is being dropped and it hit the force sensor. When it hits the force sensor will apply a force on the ball upwards. So the impulse will be upwards. So this is the direction we need to indicate here, that it is 0.481 upwards. So in 4.4, if the velocity of the ball just before it hits the force is 5.42, so VI is equals to 5.42 meters per second downwards. Calculate the velocity with which the ball will bounce off the sensor. So we're looking for VF. What is VF? That's what we're interested in. We need the mass of our softball. The mass is equals to 50 grams, which we're going to divide by 1000 to convert to kgs. And what else do we have? We have the impulse. Delta P is equals to 0.481 upwards. So VI is downwards. we can substitute it with a negative sign because it is downwards, and then the impulse is upwards, so we're gonna substitute it with a positive sign. That's if we take up as positive. You can take down as negative, and you can take down as positive and do it the other way around. Anyway, stories. So f net multiplied by the time is equals to the change in momentum. So what is f net multiplied by the time? That is 0.481. This is equals to the change in momentum. The mass multiplied by Vf minus Vi. So we're going to have 0.481 being equals to 50 divided by 1000 multiplied by Vf. Vf is what we're interested in. Minus 5.42. The first thing we should be doing here is dividing both sides by 50 divided by 1000. If we do that, we're going to get 9.62 being equals to Vf plus 5.42. Now we just need to take 5.42 to the left hand side. We're going to get Vf being equals to 4.2 meters per second upwards. That is our final velocity. 4.5, the only question that was a bit tricky. Everything else is just the basic stuff. So let's go ahead and take a look at 4.5. The ball is now replaced with a harder ball of the same size and mass. Will the force on the force sensor increase, decrease, or remain the same? The force is going to increase. Let me show you why. We know that F net is equals to the change in momentum divided by the change in time. If instead of using a softer ball, you use a harder ball, delta T is going to decrease. The time of contact is going to decrease. So if the time of contact decreases and the change in momentum stays the same, then it is easy to see that F net is going to increase. F net is inversely proportional to the time of contact. So the answer to 4.5 is increases. Write down the horizontal speed of the brake just before the girl catches it. So here on the question statement, we are told that the girl, she catches a brake of mass 5 kg, which is thrown vertically downwards from the top of a high wall. So the brake is thrown vertically downwards from the top of a high wall, right? So if a brake is thrown vertically downwards, then it has a horizontal speed of 0 meters per second, right? Because it's only moving along the horizontal. So the answer for 4.1, we're going to have Vx, x being for horizontal, being equals to 0 meters per second. And then now moving to the next question, 4.2. 4.2 is saying that let's calculate the girl's speed just before she catches the brake. Let's calculate the girl's speed just before she catches the brake. So let's go through the question statement and have an idea of what is going on. So we are told here that a girl on roller skates of combined mass 52 kg moves horizontally at a certain constant velocity. So we have some mass which is equals to 52 kgs, and then the velocity is unknown, right? And then goes on to say that she catches a brake of mass 5 kg. So we have a mass of the brake which is equals to 5 kg. It's been thrown vertically downwards, so it has a horizontal velocity of 0, like we've deduced in 4.1. And then the girl continues to move in a straight line at a speed of 2.4 meters per second after catching the brake. So when we have the girl of mass 52 kgs plus the brake of 5 kgs, they move together at a velocity of 2.4 meters per second, right? Which law are we going to use to solve this problem? We're going to use the conservation of linear momentum, right? So that is to say that the momentum before, the sum of the momentum before will be equals to the sum of the momentum after. So let's go ahead and try calculate the momentum before. So before, we have a mass of the girl, right? And then it's moving at a certain velocity, and that will be the momentum of the girl, plus the mass of the brake. It's moving at a certain velocity, and then that will be the momentum of the brake. And then after the girl catches the brick, we now have M1 plus M2, right? The mass of the girl and the brick, and then they're moving at the same velocity, right? So what is the mass of the girl? We know fully well that the mass of the girl is 52 kgs, and then the velocity initially before catching the brick, it's unknown. It's what we're looking for. And then plus the mass of the brick, which is 5 kgs, and then multiply by the velocity of the brick before the girl catches it. We're interested in the x component, so we're going to have 0 here, and then this will be equals to obviously the mass of the girl plus the mass of the brick, that will be 52 plus 5, multiplied by the velocity at which they're moving at. So we have multiplied by 2.4. So 5 multiplied by 0 is going to be 0, right? So we're going to just be left with 52 multiplied by the velocity of the girl before catching the brick. So if we solve for that, right, we're gonna get a velocity being equals to 52 plus 5 multiplied by 2.4, and then everything divided by we divided by 52, the coefficient of v, and then the answer here is 2.6308 meters per second to the direction the girl was initially moving at, right? Yeah, this question doesn't really say a lot about the direction, whether the girl is moving to the east or the girl is moving to the right. But since the question says speed, we can just forget about the direction and just write the magnitude, right? And then now let's move to 4.3. So what do we have here on 4.3? The girl brick combination moving at 2.4 meters per second moves on to a rough surface. She comes to rest after moving 2 meters along the rough surface. And then 4.3 is saying that let's write down a pair of action reaction forces acting while the girl catches the brick. So when the girl catches the brick is going to apply a force on the girl, right? So we're going to have the weight of the brick, and then a force opposing the weight of the brick. That will be the normal force of the girl's hands, right? Because the brick is going to lay on the girl's hands. The reason why the brick doesn't go and hit the ground, it is because the girl is holding the brick and exerting a normal force, because we know that if you put an object on top of another, then there's going to be a normal force. So we have a normal force there exerted by the girl's hands, right? And then another pair, we can start with Fg, the force of gravity, right? The force that the earth is pulling the girl with. We know fully well if the earth is pulling the girl, then the girl is also pulling the earth. So we have that force there. And then those are our action reaction pairs. And then now moving to 4.4. So let's solve 4.4, right? The question is saying that let's calculate the magnitude of the net force exerted by the rough surface to bring the girl brick combination to a stop after 2 meters. So let's look at the information that we have and see what we can do, right? So we know that after the girl catches the brick, they start off at an initial velocity of 2.4 meters per second. And then they come to a complete stop. So we have VF being equals to 0 meters per second. And then what else do we have? We have the mass of the girl brick system. So that will be 57 kgs, right? And then we're looking for Fnet, right? So based on the variables we have here, you can easily see that Fnet, we can find it using Newton's second law in terms of momentum, right? So we have delta P divided by delta T, right? So Fnet is equals to, so what is delta P? The mass multiplied by VF minus VI, right? So we have VF minus VI divided by delta T. So let's just go ahead and substitute and find our answer real quick. So the mass will be 57 kgs. VF is 0, they come to a complete stop, and then VI is 2.4, and then divided by delta t. Right, now we have a problem. We need delta t and we don't have it. So how can you calculate that? Let's look at the variables we have again. We have vf, we have vi, and then apart from that we have delta x, right? And then we're looking for delta t. So which formula can we use to find delta t? It should be easy to see that we can say that delta x is equals to vf plus vi divided by 2 multiplied by delta t, right? Yeah, very rarely do we use this formula, but then yeah, look at us now, we have to sort of use it. So delta x is 2, vf 0, vi 2.4 divided by 2 multiplied by delta t, right? So we divide in both sides by the coefficient of delta t. So delta t, so we have delta t is going to be equals to what? 2 divided by 2.4 divided by 2. So our delta t is 1.6667 seconds, right? So now we can substitute this delta t on the equation we had, right? So if we do that, we're gonna have f net. So we have f net being equals to 57, and then 0 minus 2.4 divided by delta t, which we now know is 1.6667. And then if you put that in your calculator, we shall get minus 82.0784, right? So we can just say 82.0784 newtons. And then we don't have to think about the direction because the question said the magnitude. Let's just leave it like that. Question 4 says a simple rocket system consists of 2 parts. A of mass 3m. So let me jot that down. So we have A, and then they're saying that the mass is 3m kg or some unit, and then B of mass 2m. So we have B, which is mass of 2m kg or some unit. I'm not so sure. As shown in the diagram, below, B is stacked on top of A, and if you look on the left hand side, there it is. Before the collision, B is on top of A, and then after the collision, A is going down, and then B keeps on going up, I'm assuming. 4.1 says state the principle of conservation of momentum in words. That is just the total linear momentum in an isolated system is conserved, right? The sum of momentum before is equals to the sum of momentum after in an isolated system. And then 4.2 says the rocket is traveling vertically upward at a constant speed v. So let me write that down. A, when it's with B, their velocity, let me write that down. The velocity is 1 divided by 3 v. No, it's actually, the velocity is v, I'm sorry. When an internal explosion causes A to move downwards at a speed 1 divided by 3v. So there's a explosion, an internal explosion, and now A is moving downwards at v equals to 1 divided by 3v, right? And then for B, we don't know what is going on. And then the question says, okay, ignore all external forces on the rocket. The question now says calculate the velocity of B in terms of v immediately after the internal explosion. So this is our scenario. Let me get it. This is our scenario before the explosion, and then this is what we have after the explosion. So this momentum here before is supposed to be equals to this momentum here after. That's what the conservation of momentum states that the sum of the momentum before is equals to the sum of the momentum after, if the system is isolated or is closed. And then the question says ignore all the forces on the rocket. So that tells us that the system is closed. Okay, so before the masses are together, right? So that will be m of body A plus m of body B, and then they're traveling at the same velocity. That's what the question states. And then after they're saying that A goes down, so we'll have m A, the mass of A, and then the velocity of A, which we are given. Now that they've exploded, they're no longer together, so the masses are apart. So we're going to have the mass of B and then the velocity of B. The mass of A is said to be 3m, so we're going to put 3m plus the mass of B, which is 2m, and then the velocity is just given as v, so that's exactly what we're going to have. The mass of A, we've already said that is 3m, and then the velocity of m is 1 over 3 v. But then I want you to realize that A is going down, and common sense says we always take up as positive. If you take down as positive, that's fine, but then to me it doesn't make sense. Up is positive. So because A is going down, instead of 1 over 3v, I'm going to put minus 1 over 3v, right? Minus 1 over 3v plus m of B is 2 meters. So, it's 2m, I'm sorry. So we're going to have 2m multiplied by the velocity which we are interested in. So that's what we are supposed to find. So 3m plus 2m will give you 5m, then multiply by v, that's 5mv, right? That's our left hand side of the equation. Then 3m multiplied by minus 1 over 3v, that will give you minus 1v, right? So, minus 1mv, right? Because this 3 here on the denominator is gonna cancel out with this 3. And then plus 2m v. Let's denote this as v of b so that we don't confuse our variable v with the v of b we're trying to determine. So the next step is to take this term here to the left hand side so that we can isolate v of b. So we're going to have, when it goes to the other side, it's going to change its sign, obviously. So we're going to have 6 m v equals to 2m v of b. We divide both sides by 2m so that we can isolate v of b. Divide by 2m. Yeah, we're going to be left with 3 here, because 6 divided by 2 is 3, right? So this will imply that v of the body B is equals to 3v. The question says we must find it in terms of v, so that is what we're going to find. So it's 3v upwards because we taking up as positive. That's how we do the problem. It's not really complicated, apart from the fact that now we have a vertical. We're working on the vertical, and usually on momentum and impulse, you're working on the horizontal. But then apart from that, it's just straightforward. The masses are joined initially, and then after that they're separated. So for EP before, you're going to add the masses and have one velocity, and then for EP after, you're going to have the separate masses with the different velocities. Yes, I think I should do a separate introductory video on momentum and impulse. So You can let me know in the comment if that's something you'd be interested in. So if we move ahead, we have 4.3, which says the graph below shows the average force exerted by A on B during the internal explosion as a function of time. And there we have it. On the y-axis we have average force, and then on the x-axis we have time. The question says, name the physical quantity represented by the area under the graph. So to calculate the area under the graph, you have to multiply the length by the breadth, right? Assuming that the length is going up, then it means you're gonna have force, the average force. So force average multiply by the time, right? But then the time doesn't start at 0, so it's basically delta t, because you have some time initial and some time final. And then which quantity is given by f average multiplied by delta t? That is delta p, right? So the physical quantity represented by the area under the graph is impulse, change in momentum. So that is coming from the formula. So this is what the question is asking for, right? So that is coming from the formula F net equals to delta P divided by delta T. So let's move ahead. 4.4, it says redraw the graph in your answer book on the same set of axes. Sketch the graph on the average. Sketch the graph of the average force that B exists on A as a function of time. So let me just put in an axis there. So there's our Y, there's our X, and then so we have force average, and then we have time in seconds, right? And then that's F A on B, right? The question says find FB on A. Newton's third law says that if body A exerts a force on body B will exert a force on body A of equal magnitude, but then in the opposite direction. So because this graph is on top of the x-axis, we're just supposed to draw the same thing, but then below the x-axis, so that the force has a negative sign, right? Equal magnitude, but opposite direction. So these two are supposed to be equal, this part and this part. And that's it for this question. If you like the video, please subscribe. Trolley X of mass 1.2 kgs travels at 8 meters per second east and collides with trolley Y of mass 0.5 kg, which is initially at rest. And then the velocity time graph below shows the velocity of the trolley X before, during, and after the collision with trolley Y. And then we have a fancy sketch there. And then the first question, 4.1, which is saying let's state the principle of conservation of linear momentum. We'll leave that for you. And 4.2, 4.2.1. So for 4.2.1, we're looking for the velocity of trolley Y immediately after the collision. So how can we possibly determine the velocity of trolley Y immediately after the collision? We are going to use the principle of conservation of linear momentum, because we know fully well that the sum of the momentum before a collision should be equal to the sum of the momentum after a collision, right? So what is the momentum before a collision? We're going to have the momentum of trolley X plus the momentum of trolley Y, and then after the collision we're gonna have the sum of momentum of trolley X plus the sum of the momentum of trolley y, right? So if we calculate the sum of the momentum of trolley x, let's not forget that p is equals to m multiplied by v, right? We're gonna have 1.2 multiplied by 8. So now we can see that we need to decide on the direction. So let's take direction to the east as positive, right? And then the trolley, the momentum of trolley y, it is at rest, right? So we have 0.5 multiplied by 0, right? This will be equals to the momentum after the collision of x. We have 1.2 multiplied by the velocity. The velocity is on the graph, right? Because here, this is the velocity before the collision, during the collision, and then immediately after the collision. So we have 4 then, and then plus 0.5 multiplied by the velocity of trolley y, right? So without wasting any time here, we're gonna say that the velocity of trolley y should be equals to, so we have this 1.2 multiplied by 8 there, so we're gonna have 1.2 multiplied by 8, and then this, because we're multiplying by 0, is gonna fall apart, right? And then minus this here, which is just 1.2 multiplied by 4, and then everything divided by the coefficient of Vy, which is 0.5. So if we put that in our calculators, we shall get Vy is equals to 9.6, right? We take in direction to the east as positive, so this will be 9.6 meters per second. To the east, right? To the east. And now let's do 4.2.2. So 4.2.2 is saying that let's find the average net force that trolley X exerts on trolley Y during the collision. The average net force that trolley X exerts on trolley Y during the collision. We already know that after the collision, trolley Y is going to move to the east, right? So the direction of this net force should also be to the east, right? Irregardless of the sign we're going to get in our calculation, right? Because the sign is going to depend on which body you use, right? Are you using trolley X or are you using trolley Y? But then that shouldn't have an effect on the magnitude, right? So if we use trolley X, right? So we're going to say F net is equals to delta P divided by delta T. Let me explain why I'm using trolley X instead of trolley Y. The velocity of trolley Y, we calculated it ourselves, right? So what if that velocity is wrong and then we use it again, right? There's a good chance that that answer will also be wrong, assuming that there's no positive marking. So let's just stick to trolley X because we're going to be using the velocities that are given to us. So there's no way we can go wrong with the values, right? Momentum final will be 1.2 multiplied by 4. Minus momentum initial, which is 1.2 multiplied by 8, and then divided by the change in time, which I've indicated here in our graph, right? It happens from 20.1 to 20.2 seconds. So here we're gonna have 20.2 being the final minus 20.1 being the initial. So if I just put that in my calculator, let me see what I get here. I'm getting minus 48, right? But we've already said that we don't care about the sign, right? We know that it's supposed to be 48 newtons to the east, right? To the east. And yeah, I think that's it for 4.2.2. Let's see what we can do for 4.3. So 4.3 here is saying that let's determine if the collision is elastic or inelastic, right? And explain the answer by means of a suitable calculation. So what is the prerequisite for an elastic collision? So if a collision is elastic, then we need two things to be conserved, right? We need the momentum to be conserved, and we need the kinetic energy to be conserved. So in 4.2.1, we calculated the value of y, assuming that momentum is conserved. So it wouldn't make sense if we calculate the momentums again, right? Because that's what we're assuming. We're assuming that the momentum is already conserved. So we're just going to calculate the kinetic energy and see if it is conserved, right? Yeah, so let's go ahead and do that. So we're going to say EK before and then calculate that and see if it's equals to EK after. So EK before will be equals to just the kinetic energy of trolley X, because trolley Y was stationary. So when I have 1.28 and squared, right? So if I just put that in my calculator, I have 1.2 multiplied by 8 squared, and that is 38.4 joules, right? And then EK after, now I have 1.2 multiplied by 4 squared, plus this is for our trolley X, right? Plus the EK for our trolley Y. We have the mass, which is what is the mass again? The mass is 0.5, so we have 0.5 multiplied by the velocity, which we calculated, right? 9.6, and then we square that. So let me just put that in my calculator real quick and see what I get. So multiply by 0.5 multiplied by 9.6 squared, I'm getting 32.64 joules. So since, you know, EK before is not equals to EK after, then we deem this collision inelastic, right?